Welcome to qnawire.
So this would be for part A, r squared in meters squared, of course, versus the gauge pressure. Here it is measured in atmospheres instead of pascals. That is why we have such numbers. And so this is essentially using Bernoulli's equation and then the kinematics of free fall motion. So now we can, this is the graph, but furthermore, how do we get to that graph? So for part A, we're applying Bernoulli's equation. Applying Bernoulli's equation between the top and the bottom of the liquid in the tank gives us that the atmospheric pressure plus the gauge pressure plus the density times g times h would be equaling 1/2 rho v squared plus, again, the initial pressure. We're going to, of course, cancel these out, and we're getting that the gauge pressure plus rho gh is equaling 1/2 rho v squared. And the free fall motion leaving the tank gives that the range r is equaling the velocity times t, and that y, due to kinematics, would be 1/2 gt squared. And we know that y here is equaling 50.0 centimeters. Eliminating t from both of these equations gives us that we can say v squared is equaling rho g divided by 4y multiplied by r squared. We're going to put this result into, essentially substituting this result into the Bernoulli's equation, and we can say that then the gauge pressure plus rho gh would be equaling, now it would be rho g over 4y divide close parentheses multiplied by r squared. And so this would, of course, give us a we're going to solve for r squared in terms of h, and we can then say that r squared is giving us 4y over rho g times the gauge pressure plus 4yh. As you can see here, this somewhat looks like y equaling mx plus b, where here the slope is equaling 4y over rho g, and then the y-intercept b is equaling 4yh. And this is essentially how we are plotting this graph here. And again, the gauge pressures in atmospheres. So that is how we were able to even plot, and that's why it was giving us a straight line, because we know that this is the slope is this is going to give us a straight line slope. And so we can then say that if we wanted to find the best line fit, you can find you can use Excel or MATLAB to find the best line fit for this graph. For part B, we can then say that r squared would be equaling, this would be 25.679 meters squared per atmosphere multiplied by the gauge pressure, and then plus the y-intercept of 16.385 meters squared. This would, of course, be somewhere around here, and that does, that is in line, rather, with this linear slope. And so at this point, we can then solve the y-intercept in terms of h. And so we can then say that 4yh is giving us 16.385 meters squared. And we can then say that h would simply be equaling 16.385 meters squared divided by 4 times y. Y is, again, 50 centimeters, so we can say 4 times 0.500 meters. And we find that h would be equaling approximately 8.2 meters. This would be our answer for part B. And then we want to then find the density of the liquid. So we can say that the density is going to be equaling 4y divided by the acceleration due to gravity times the slope. We can simply say slope. And so this would be equaling to 4 times 0.500 meters divided by 9.8 meters per second squared multiplied by 25.679 meters squared per atmosphere. And again, this should, of course, be dimensionally correct, but we have atmospheres. So we need to multiply this by 1 atmosphere for every 1.01 times 10 to the 5th Pascal. So this needs to be dimensionally correct. And the density of the liquid is then found to be 803 kilograms per cubic meter. This would be our second answer for part B. That is the end of the solution. Thank you for